As we embark on the study of chemistry, the study of the elements and their interactions, one of the most useful tools that we will employ throughout our journey is the periodic table. You have already gone through a laboratory exercise where you developed your own periodic tables. You looked at the first 20 elements, you looked at a certain set of properties of those 20 elements, and you began to fashion groups from those properties and try to align them according to their relatedness. So what I'm going to do, though, is look at chemists throughout the decades, throughout the centuries. How did they approach the very same problem, and how did they come to understand that the elements really do have a periodicity as regards their chemical and physical properties, and how do we depict that relatedness to make it useful and allow us to make predictions, which is what chemists and scientists always look for. They want their tools to help them predict what should be taking place. So let's look at, first of all, Antoine Lavoisier. He was a French chemist, very prominent chemist, very prominent scientist. He is a person that we will come back to repeatedly throughout the year and discuss his contributions to the field of chemistry. Beyond just what I'm going to discuss about the periodic table, Lavoisier's probably his biggest role was helping to facilitate the transition of the field of chemistry from a purely qualitative kind of study and quantifying it. And by making it more quantifiable, being able to tease out, ferret out more information and be more precise with that information. Now, in regards to the periodic table, the key aspect was that at his point in time in the 18th century, there were 33 known elements, and he was one of the first people to start to comprise a list of what would be considered elements. He also was known for helping to distinguish two major groupings of elements, the metals and the nonmetals. Lavoisier, we will come back and talk about him again throughout the course. Going a little further down the line, we encounter Johann Dobereiner, who was a German chemist, and during his lifetime there were about 50 or 60 known elements. He too began to approach those elements and try to see if there was a relatedness in their properties. And he devised a grouping plan known as triads. He noticed that you could take elements and group them in threes. And he called these threes triads. And the members of the triad, he noticed, had very similar chemical and physical properties. He noted that when you arrange the three members of a given triad according to increasing mass, the middle element had an atomic mass that was essentially equal to the average or the mean of the atomic masses of the lightest and the heaviest of the triad. It also was true about the properties, that the middle element had properties that were somewhat in between, again, the extremes, the lightest and the heaviest of elements. Let's look at some of his triads. One of his triads was made up of lithium, sodium, and potassium. Now, lithium has an atomic mass of 6.94 AMUs. Potassium, the heaviest of the triad, has an atomic mass of 39.10 AMUs. And when you take the average of those two, you get 23.10 AMUs. And if you compare this to the middle element, sodium, it has an atomic mass of 22.99 AMUs. Very, very close to the mean of the lightest and heaviest. If you recall, these were three of the metals that we looked at in a demonstration that I did in front of the class. And sodium, not only being in the middle as far as mass, is also in the middle as far as the properties. If you think particularly when I added these to water, that sodium was not as reactive as potassium, which instantly burst into flames, but was more reactive than the lithium that mostly just bubbled and gave off lots of heat. So this idea of triads holds up, at least for this first triad, lithium, sodium, and potassium. Another triad that Dobereiner devised was made up of calcium, strontium, and barium. And calcium has an atomic mass of 40.08 AMUs. Barium, the heavier one, is 137.33 AMUs. Their average is 88.71, and you can see that is pretty close to the atomic mass of strontium at 87.62 AMUs. So it holds up again here, this idea of triads for the second triad. A third triad that he devised was made up of chlorine, bromine, and iodine, which showed similar kinds of results. But once we get beyond those three triads, it doesn't really work very well. The other triads that he devised start to fall apart. They're not nearly as related as we see in the three I just mentioned, and it just simply doesn't extend far enough through, as I said, the 50 or 60 known elements. So we're starting off on the right path, but this clearly is not the final solution. A little bit later, John Newlands arrives on the scene. Newlands was a British chemist, and he too was approaching the elements, looking for physical and chemical properties, seeing if there were similarities. He studied the properties of, again, 60, 70 different elements very thoroughly, and what he noticed as you arranged them from lightest to heaviest, he noticed that there was a pattern that started to emerge. And the pattern that he noticed was that roughly every 8 elements, there was a repetition. That the chemical properties like density and physical appearance, color, consistency, they started to repeat themselves, and definitely the chemical properties. So he called this his law of octaves, and it worked pretty well as long as we were dealing with the first 20 elements. But the problem that he ran into, once you got past calcium, once you got past the first 20, the relatedness did not hold up as well. And his mistake generally is agreed upon that he forced the subsequent elements into the 8 groups that he had identified. So whether they truly fit or not, he simply forced them into the pattern that he had identified, and again it starts to fall apart. So we made a good leap forward. We got a little more refined way of grouping the elements, but this isn't the final solution. We're on the right path, but this isn't quite it. Then along comes Lothar Meyer, a German chemist, and Dmitry Mendeleev, a Russian chemist. They were contemporaries of each other. They would have known about each other's work. They would have read each other's papers. They probably didn't directly confer with each other. They worked in separate laboratories, but they both had a similar approach. They took Newland's work and they recognized that he was onto something. So they took roughly his approach, but where they differed is when an element didn't fit into one of those 8 groups that Newlands had identified, they didn't put it into that group. They looked for another group that would have matched the properties more closely. So they were very, very strict that the elements really had to be related to each other. They weren't going to blindly place elements into the groups. Now, the upshot of this is, of course, that there were gaps that started to appear in their table. They weren't thrown off by that fact. They were not disconcerted by that. They understood that the likelihood was that there were elements that had not yet been discovered that would end up fitting into the gaps that were starting to emerge. And sure enough, as more elements were discovered, they did fit into those gaps. And Mendeleev probably gets the bulk of the credit here. He was incredibly meticulous about examining properties and being very faithful to their relatedness before he would group them. So he's probably the more prominent of the two chemists here, but they both essentially came to the same conclusion about the same time, completely independent of one another. So their periodic table would be very close to what we're picturing in our periodic table, the one that you see up on the wall of the chemistry laboratory. A little bit later, along comes William Ramsay, another British chemist. His key contribution was that he meticulously analyzed the components of air, and he pretty much almost single-handedly over a couple of decades, he discovered these inert gases. He discovered pretty much all of the noble gases through the work in his laboratory. The placement of these noble gases into the periodic table seemingly bolstered the work of Newlands and Meyer and Mendeleev and seemed to enhance our view of the validity of this periodic law that clearly was emerging. So his work was integral, again, in getting us to the present two-dimensional grid-like arrangement of our modern periodic table. But the story wasn't over just yet. In the early 20th century, Henry Moseley, another British chemist, felt that there was more to the story, and he actually developed a technique where he could use what's known as X-ray spectroscopy. He could use the data as he analyzed the different elements, and he was able essentially to come up with the atomic number for the elements. Up to this point, atomic numbers were considered just to be sort of arbitrary values just assigned to the elements. And he, through his very meticulous analytical and quantitative work with spectroscopy, showed that there was actual measurable value that the atomic numbers represented. And so it actually was related to the physical makeup of the elements. So today's periodic table is related to the work of Moseley and Meyer and Mendeleev, that the elements are arranged according to increasing mass, but increasing mass because they're arranged according to atomic number, the number of protons in the nucleus of those atoms, and that was more important than simply the mass. It was the atomic number, the number of protons. Also, if these atoms are neutral, that's going to be the number of electrons. It's really about the electrons. Now, unfortunately, the problem for Moseley was he was a young guy. Britain was involved in World War I, and he felt compelled to enlist in the army, and he was killed by a sniper in 1915. A huge, huge loss to the scientific community. A very brilliant chemist. Who knows the work that he would have done had he lived, but again, he felt duty bound that it was important to go off and be part of the war effort. Now, wrapping up the evolution of the periodic table, I want to mention Glenn Seaborg. Seaborg was an American chemist. He was part of the U.S. atomic bomb project known as the Manhattan Project, and he was given a very specific task in that group. They were trying to isolate and purify plutonium-239, which in the second bomb that the United States dropped on Japan was a plutonium bomb. But that was his main work. He was studying radioactive isotopes, essentially. And so he plays a huge role in the discovery of most of the transuranium elements. Those are all of the elements after uranium that are artificial elements. They pretty much exist in the laboratory. So he plays a big role in the completion as we continue to expand the periodic table. And he was honored by having element 106 named after him, Seaborgium, for his work over the decades. Now, our periodic table then looks like this. The typical grid, you see the group numbers here are 1 through 18. The more classical model we talked about in class, using Roman numerals to enumerate the groups or families. You can see the numbering down the left-hand side of the table, numbering the different periods of the periodic table of the elements. This is pretty much what you see in your folder and what you see up on my wall. And the elements are named all the way through 118. They all have formal names at this juncture. But these are not the only ways to depict the periodic table. This is what you would see in every college laboratory, every high school laboratory throughout the decades. Classical two-dimensional grid. The problem is it doesn't always depict the relatedness of the elements very effectively. And so there are many alternative tables that do a better job at depicting the relatedness and the transition of properties, all kinds of different properties that we could talk about that we will discuss a little bit later, but they do a better job of depicting the relatedness and what the patterns are. For example, this oval-shaped table is much more effective in looking at things like electronegativity and ionization energy and electron affinity and other properties too. Our two-dimensional grid presentation, there are some jarring problems with it that do not reveal the cyclic aspects of these properties that I just mentioned. Another really popular one, and Seaborg really particularly liked this one. This is the Alexander table, and you can see that it is three-dimensional, and it too is much more effective in depicting the properties of all of the elements, how related are the elements, and how these properties vary, what the pattern of variance is as you move down a group or across a period. So there are many other periodic tables, pretty much what you see in your textbook and what you see on the wall. As much as anything, it is for convenience that it is in that two-dimensional grid-like arrangement. But please understand that as effective as it is, there are some drawbacks in trying to make it more convenient to present the information in that kind of flattened method. That is the periodic table.